Have you ever wondered how some systems can verify, let's say, thousands of digital signatures without completely breaking the bank? Well, today, we're going to unpack the cryptographic engine behind that kind of magic. It's an incredibly powerful, but surprisingly simple data structure called a Merkle Tree. And believe me, it is quietly changing the game for digital trust. So let's dive right in.
Okay, so let's start with the central challenge. Imagine you need to lock in, say, 10,000 signed documents onto a blockchain. Make them permanent, verifiable, the whole deal. Now, the most obvious way to do this is to just record each one by one. But, as you're about to see, that simple, obvious answer, well, it leads to a huge cost problem.
And this is where the numbers get kinda wild. Look at this. Storing each document's proof individually, you're talking about 10 cents a pop. For 10,000 documents, that's $1,000 right there. But then look at that bottom row. Using this thing called a Merkle Root, you can anchor a practically unlimited number of documents for 3 cents. Total, not 3 cents each, 3 cents for everything. So how on earth is that even possible? Well, here's the beautiful core idea. Instead of juggling thousands of these individual digital fingerprints, what if we could cryptographically roll them all up into one single master fingerprint? Just one piece of data that represents the entire collection. This is the elegant solution to our crazy cost problem.
So let's pull back the curtain and see exactly how this works. We're going to build this thing from the ground up, and it all starts with one of the most fundamental building blocks in all of cryptography. And that building block is the cryptographic hash. The easiest way to think about it is like a unique fingerprint for any piece of digital data. You can feed any document, a tiny text file, a massive novel, into a hash function, and it always spits out a unique, fixed-size string of characters. What's so crucial here is that the same document always gives you the exact same hash. But, and this is key, you can never ever use that hash to figure out what the original document was. It's a one-way street. Okay, so here's the construction process. It's pretty straightforward. Step 1, we take every single one of our documents and we hash it. These initial hashes become the leaves of our tree, the bottom layer. Step 2, we start pairing them up. We take the first 2 leaf hashes, combine them, and then hash that combination to create a new parent node above them. We do this all the way down the line for all the pairs. And step 3 is, well, you just keep doing that. You take your new layer of parent hashes, pair them up, hash those pairs, and just keep building the tree level by level. And you keep going, hashing and pairing all the way up until you're left with just one single hash at the very top. This is it. This is the champion, our master fingerprint. And it has a name, the Merkle Root. This one single hash now cryptographically represents every single document we started with. So we've built the tree, which is cool, but its real power, its magic, isn't just in summarizing data. It's in how it reacts when something changes. And this is where things get really, really clever. The secret ingredient here is a property of crypto hashes called the avalanche effect. It's a pretty wild concept. It means that if you change even one tiny little bit of the original data, I mean, a single comma in a contract, one pixel in a photo, the output hash doesn't just change a little bit. No, it changes completely. It becomes a totally different, unrecognizable hash. All right, so let's put this to the test. Let's say some bad actor gets their hands on just one of our thousands of documents, and they make a tiny little change. They change a comma to a period, something nobody would ever notice. What does that tiny change do to our final Merkle root? And bam, here's the result. Because of that avalanche effect, that tiny comma change creates a completely new leaf hash at the bottom. That new hash then changes its parent's hash when it gets paired up, and that change just ripples. It cascades all the way up the tree, level by level, resulting in a final Merkle root that is totally and completely different. Any attempt at tampering is immediately obvious because the new root will not match the original one we stored on the blockchain. There's no hiding it. Okay, so the tree is incredibly tamper-evident. That's its first superpower. But it has another one, and it's all about incredibly efficient verification. Let's see how that works. So here's the next puzzle. Let's say you need to prove to somebody that your specific contract was part of that original batch of 10,000. Do you have to send them all 10,000 documents just so they can check? Or even all 10,000 hashes? I mean, that would be super inefficient and frankly a privacy nightmare. And the beautiful answer is no, absolutely not. You don't need the whole tree. To prove your document belongs, you only need to provide a very small, very specific set of other hashes. These hashes make up the direct path from your document's leaf all the way back up to the root. And this is what we call a Merkle proof. Let's make this super concrete. Say you want to prove document C was in the set. Okay, so first you provide the hash of document C itself. But for the verifier to calculate the next level up, they also need its partner, its sibling, which is the hash of document D, so you provide that too. Now the verifier can hash C and D together to get their parent hash. Great. So what do you give them next? You give them the sibling of that parent, which is the hash of A and B combined. The verifier then takes the parent hash they just calculated, combines it with the sibling you just gave them, and hashes that. If the final root they calculate matches the official one on the blockchain, boom, your proof is valid. You've just proven document C was in the original set without revealing anything about A, B, or D.
And just how efficient is this? It's mind-blowing. For a tree with 1 million documents, the entire proof, all the hashes you need to provide, is only about 640 bytes. That's it. For comparison, if you had to present all the hashes, you'd be sending over 32 megabytes of data. We're talking about an absolutely exponential improvement in efficiency. It's just insane.
So we've seen that Merkle trees are secure, they're wildly efficient, but let's zoom out for a second and talk about the big picture. Why does this clever piece of tech actually matter so much?
Well, because it fundamentally changes how we think about trust. Right now, for so many things, we have to trust a central company. We trust them not to alter our records, not to get hacked, not to just go out of business. This technology allows us to shift that trust away from a fallible human institution and place it directly onto open, transparent, verifiable mathematics. The trust is in the code, which literally anyone can go and inspect for themselves.
I love this quote because it perfectly captures this new way of thinking. It's a fundamental shift away from just trust us, we've got it, towards don't trust us, verify it for yourself. The blockchain holds the ultimate truth, the root. The Merkle proof provides the data, and anyone, anywhere, can run the numbers and confirm the truth.
And that really leaves us with a final big question to think about. When our most important records, our contracts, our property deeds, our educational certificates, can be anchored in a way that is permanent, public, and can be independently verified by anyone on the planet forever, what does that do to the future of trust? What new kinds of collaboration and verification does that unlock for all of us?